In this class, we will discuss about one function called Airys stress function in two dimensions. So that means it's a function of x and y. So for solving two-dimensional cartesian problems, there is of course cartesian coordinates x and y dimension. For solving some of the problems in elasticity of two dimensions in cartesian coordinates, sometimes we make use of one type of stress function called Airy stress function, which was derived by the person Airy. So it is defined like this. So it is denoted by phi. So phi is a function of x and y. So it is defined like this. Using the Airy function, you can always find out the stress components in two-dimensional stress system. So in 2D stress system, you will be having three stress components: sigma x, sigma y, normal stress components, and low x, y shear stress component. So you can always express these three stress components in terms of Airy stress function like this. Sigma x is given by dou square phi by dou x square, that is second derivative of phi with respect to y. And sigma y is given by dou square phi by dou x square, that is second derivative of phi with respect to x. And dou x y shear stress is given by minus dou square phi by dou x dou y. That means we have to differentiate phi with respect to x once, and then we have to differentiate with respect to y. Now, by knowing the stress function, we can always find out the stress components sigma x, sigma y, sigma z using these three partial derivative formula. But one condition is there: all the functions cannot be phi functions. So if at all you want to have a phi function, it should satisfy one equation called biharmonic equation. So phi should satisfy this biharmonic equation. So which is given by this. So phi should satisfy this biharmonic equation. Harmonic means it is second degree. Biharmonic means it is fourth degree. So here you can see that this is the biharmonic equation. Dou power 4 phi by dou x power 4 plus 2 times dou power 4 phi by dou x square dou y square plus dou power 4 phi by dou y power 4. This should be equal to 0. So this can also be expressed in another form like this: del square 4 phi is equal to 0. Actually this is del, so you can call this as del, Greek symbol. So del power 4 phi is equal to 0, or this del power 4 can be split as del square into del square phi. Del square of del square phi is equal to 0. Like this you can write. So these two are same. And this del power 4 can be written like this. This is nothing but your del power 4 without this phi. And del square is this one: dou square by dou x square plus dou square by dou y square. This is called as del square, which is also called as the Laplace operator. So Laplace operator is del square, that is dou square by dou x square plus dou square by dou x square in two-dimensional stress system. So if the phi expression or the phi function satisfies this equation, then it is a Airy stress function. Suppose in any problem they may give the function phi, they may ask you to check whether that phi is a Airy stress function or not. So if you want to check whether the given function phi is Airy stress function or not, you have to take this LHS. So differentiate that phi 4 times with respect to x, differentiate that phi 2 times with respect to x and 2 times with respect to y, differentiate that phi 4 times with respect to y, and then take the sum of all those three. If you get it as 0, then definitely it satisfies it satisfies the biharmonic equation, or you can say phi represents a Airy stress function. Once you prove that, then using these three relationships, you can always find out the stress components in a two-dimensional stress system, which are nothing but sigma x, sigma y, sigma tau x. Now let us take some examples for understanding the stress function. I will take always these are phi is normally expressed as a polynomial function. Polynomial means x square, x cube like that, and similarly y square, y cube like that. So if you want to take the first degree polynomial, the highest degree of x and y will be 1. So that is first degree polynomial. In the first degree polynomial, it normally it is taken as a1x plus b1y, where a1, b1 are constants which have to be found out using the boundary conditions. So here phi 1 is equal to a1 into x, the higher order of x, the higher degree of x is 1, similarly higher degree of y is 1 here. Now if you want to find the stress components for this Airy stress function, if you use this, sigma x is rho square phi 1. So here 1 stands for the first degree, that's all. Phi 1 stands for first degree. So if you see that, if you differentiate this once with respect to y, you will get b1, and if you differentiate this twice with respect to y, you will get 0. So this sigma x will be 0. Similarly, sigma y is, once if you differentiate with respect to x, you will get a1, partial differentiation this is. And second time if you differentiate with respect to x, that a1 which is constant, you will get 0. Similarly, tau xy also becomes 0. So if you want tau xy, once you have to differentiate with respect to x, like whatever you have got, that should be differentiated with respect to y, and you can see that there is also 0 here, the 0 here. That means if phi is a first degree polynomial, then all the three stress components they become 0. Then we say that first degree polynomial represents a stress-free body. Stress-free body means all the stresses are zeros. That is the meaning. Now if you take the second degree is expressed like this. You can see here phi 2 stands for the second degree. So a2 by 2 into x square plus b2 by into xy plus c2 by 2 into y square. So this is the second degree polynomial. In the examination, they will ask you to plot the stress distribution for a second degree polynomial. If phi is a second degree polynomial, draw the stress distribution, they will ask like that. So that is what I am doing here. So please remember here, it should be like this. Second degree polynomial should be like that. Means you have x term, then you have xy term, then you have y square term. This is for the second degree. In the first degree, you have one term. So x square, xy and y square. In the first degree you have only x and y. You can see here. Only x and y you have. In the first degree polynomial. In the second degree polynomial you have x square term, xy term and y square term. This a1 is associated with x is associated with a1, y is associated with b1. Here x square is associated with a square by 2 or a2 square by 2. Once again here this 2 stands for a2, b2, c2 I have taken, they stand for the second degree. So here I have taken 1, 1, a1, b1, first degree, a2, b2, c2 for second degree. So this is replaced, this coefficient of this is a2 square by a2 by 2, coefficient of this will be b2 and coefficient of this will be c2 by 2. So that's what. So if you add this plus if you put so you will get the stress function. Now for this second degree polynomial, let us calculate the stress components. Same formula we have to use. Sigma x is dou square phi 2 by dou x square. So that is what you have to do is, this meaning of this is dou by dou y of dou phi by 2, dou phi 2 by dou y. That means first differentiation you have to do, then once again we have to differentiate the second time. So this is how we are going to write. So that is dou by dou y of, what is dou phi 2 by dou y? So differentiate this with respect to y. So when you are differentiating this with respect to y partially, so x is constant. So the derivative of this will be 0. Derivative of this will be b2 into x plus derivative of this will be c2 by 2 into 2y. The 2 and 2 will get cancelled and get c2y. Now this you have to differentiate partially with respect to y. So this derivative of this becomes constant. Derivative of this becomes c2. So the value of sigma x becomes c2 now. Similarly, sigma y is dou square phi 2 by dou x square. So see here, please see the difference here. Sigma x is associated with y square in the denominator. Sigma y is associated with x square in the denominator. Dou xy is associated with dou x, dou y, x and y both in the denominator. So these three are very important relations you have to remember. So sigma y is dou square phi 2 by dou x square. That means it is dou by dou x of dou phi 2 by dou x. So what you have to do now, this we have to differentiate with respect to x partially. When you are doing that, y becomes constant. So if you are differentiating this with respect to x partially, this becomes a2 by 2 into 2x. That is a2 cancels, and derivative of this will be with respect to x will be b2 into y, and derivative of this will be 0 because y is taken as constant. So once again you have to differentiate this with respect to x, you are going to get a2. So the value of sigma y becomes a2 now. Now the third one is dou xy. Dou xy is minus dou square phi by dou x dou y. So this can be written as, so what I will do is first I will differentiate with respect to x, then whatever I get, that I will differentiate with respect to y now. So one thing is minus is there here. So minus dou by dou y of dou phi 2 by dou x. Now dou phi 2 by dou x according to here is this one only, a dx plus b to y only. But this we have to differentiate once again with respect to y. So treat x as constant. So the derivative of this will be 0. Derivative of this will be b2. So minus b2. So minus b2 is the value of shear stress component. So sigma x is c2 positive, sigma y is a2 positive, tau y is minus b2 negative. So here, so this positive value of sigma x represents that it is tensile stress. If you get negative value, you have to take it as compressive stress. So this is also tensile because positive. Then this, of course, this shear stress you are getting negative. Negative means you can show like this top face. Top face is like this. Shear force is acting in the negative direction like this. So this is how you can represent. Now, how to plot this in the form of how to plot this stress diagram. So they will ask you to plot the second degree polynomial stress diagram. So for that, what you have to do is draw a two-dimensional object with of course with very small thickness here. Thickness is taken as unity. That means you can say that it is a thin plate. So thin plate means naturally it is a plane stress problem. So in the last video I have told that plane stress problem is an example for plane stress problem is biaxial stress distribution on a thin plate. So draw a plate like this, show the thickness. Now sigma x is the stress acting in x direction. So I will take this as x direction and this as y direction. Of course, you can take you can show either like this or like this, that is material. So whatever it is, so sigma x is C2 value. Please note that this is a constant value. C2 is constant here. So the stress value remains constant in x direction. That is the meaning. And it is tensile in nature because you have got positive value. So how to show that? So I have to show sigma x like this. So this sigma x is positive value. That means it is tensile. Away from the element you have to show. Its value is C2 or it is constant. Similarly, this side also it is same. So whatever stress is acting this side, same stress is acting this side. That means your sigma x, sigma y, and dou xy, they are independent of xy. Please note that because they are all constants. All these three, they are constants. Constants means independent. They don't depend on the value of x and y. Independent of x and y. So that means they are constants. So this is how you have to show sigma x. And if you want to show sigma y is positive. That is tensile stress only. It is also constant. A2 value. So y I have to show sigma y tensile. So like this, sigma y away from the element. Here also, this side also, sigma y away from the element. Both are equal. So that means in x direction stresses are equal. In y direction also stresses are equal. They are independent of x and y. And tau xy, as already told, we have got the value of tau xy as minus b2. That is also constant. We know that shear stress always it acts complementary manner. So minus b2, I told you take the top face. So this is the top face. On this top face, negative direction. That is towards left if you show. So that is your tau xy. So minus b2 represents that it is acting towards left. So since this shear stress is acting, it will act complementary. So if this is acting like this, so one more shear stress should act like this. So these two should meet. Similarly, here since it is acting like this, at the bottom face, it should act in the opposite direction, and on the opposite face of this, it should act downwards. So the meaning of that is shear stress acting on the upper face like this, on the lower face like this, and it will be acting on left face like this, right face like this. So how to show shear stress? So they always act like this. Please note this. This is very important. So these two arrows should be. These two arrows should be. So this is how shear stress acts. This you are learned in your strength of materials also. So this is the stress distribution. We call this diagram as stress distribution diagram. So a second degree polynomial will represent stress distribution diagram like this. So you can observe in all the two cases, both the cases, phi 1 and phi 2 cases, automatically this biharmonic equation is satisfied, because if you take the fourth derivative of this, naturally it will be 0. Second derivative itself is 0, therefore third and fourth derivatives will be 0. And similarly here also, if you take fourth derivative, definitely all these three terms, this term, this term, this term, they are all zeros. From that the RHS becomes 0. Automatically it satisfies the biharmonic equation. So your first degree, second degree and even third degree polynomial, they represent automatically the biharmonic equation, because they have only x to the power of 1, y to the power of 1, x squared, y squared terms, and all of them, if you differentiate 4 times, all the coefficients they will vanish, and LHS, if you add all these 3 terms, becomes 0, and RHS also becomes 0. These are the examples for Airy's stress function. So in the exam, they will ask you define Airy's stress function. You have to write the definition like this. So in the material what I have sent, in that also it is there, and you can give some examples. Airy's stress function in terms of polynomials example, or they may give a problem also, or they will ask you to explain, sketch the stress distribution for a second degree polynomial by using second degree polynomial as an Airy stress function, or third degree polynomial as Airy stress function. Third degree polynomial also is there, fourth degree is also there, but they are all lengthy. Anyway, if you have time, you can go up to third degree. Third degree polynomial also is there, so that I have already sent in the Google Classroom notes. So module 3 notes, if you refer, you will get the third degree polynomial also. So in the next class, I will take up a numerical example on this Airy stress function and how to find the stress distribution for the given Airy stress function.